Hi, my name is Chris, and today I have the opportunity to report a strategy of constructing PN homojunctions using a spin coating solution processing technique between an N-type iron metal oxide thin film and a P-type iron chromium aluminum metal oxide alloy thin film. We will begin our discussion with what a PN homojunction is, why this type of semiconductor is of interest to electrochemists, and possible applications of fabricating semiconductors like these using in-situ extraterrestrial resources. Semiconductors have many practical uses in electrochemistry, some of which may aid in the acquisition of renewable resources. More specifically, PN-type semiconductors may facilitate the conversion of photons into electricity, providing renewable energy from sunlight. A PN semiconductor consists of a homojunction between a negative N-type material with an abundance of electrons and a positive P-type material. The P-type material can conduct the whole left when the electron from the N-type material is excited from the valence band to the conduction band. This electronic excitation is driven by the absorbance of a photon of light incident to the surface of the semiconductor. To date, the use of all-metal-oxide semiconductors in photovoltaic devices has appealed to electrochemists due to the stable nature and relative abundance of metal oxides on Earth. The abundance of precursors to all-metal oxide devices is consistent between Earth and Mars. Additionally, the lack of an oxidant in the atmosphere of Mars suggests that the use of solar energy may be more ideal than sources of fuel on Earth used to support mission goals. The use of in-situ extraterrestrial resources to fabricate solar panels, as opposed to bringing prefabricated devices across the solar system from Earth, will decrease the consumption of fuel used for the mission. The N-type iron oxide species and the P-type iron chromium aluminum oxide alloy used in this study are consistent with resources abundant on Mars that could be procured from naturally occurring hematite. These materials show potential to support future NASA mission goals of using in-situ Martian resources to generate renewable energy. Now that we have discussed the practical uses of PN homojunctions, we will review the results of this study. The formation of all-metal-oxide photovoltaic devices was strongly supported by UV-vis data measured after the first layer of solution processing, and then again after the second layer. Figure 1 represents an overlaid UV-vis spectrum of the plates made with the iron chromium aluminum alloy as the first layer, and the iron oxide film as the second layer. The dashed lines represent the data measured using the plates with only the first film present. The solid lines represent the data measured using the plates with both layers present. Absorbance values measured using the single layer plates were consistently lower than absorbance values measured using the same plates after chemically joining the second layer. This result indicated that a PN homojunction using the two metal oxide precursors was formed. Formation of the all-metal-oxide PN homojunction was confirmed by differential short-circuit current values measured by cyclic voltammetry. The measured short-circuit current values were found to correlate with different intensities of light as the plates were illuminated. The current voltage curves of the plates in a 0.1 molar sodium hydroxide solution indicated that the sequentially processed plates exhibited photocurrent. The current voltage curves are represented by figure 2. Here, current in microamps versus the standard hydrogen electrode in volts for the plates made using the iron chromium aluminum oxide layer deposited first, and the plates made using the iron oxide layer deposited first may be compared in dark and illuminated conditions. The plates made with the metal alloy layer deposited first are represented by the blue lines and data. The plates made with the iron oxide film first are represented by the yellow data. The illuminating condition is indicated by the dashed data sets. You may notice that the current corresponding to the first layer alloy layered plate was lesser when the plate was illuminated relative to dark conditions. while the current corresponding to the first layer iron oxide layered plate was greater when the plate was in dark conditions. This result was expected and can be explained by the direction that the current was traveling. The plates with the layers applied in opposite orders experienced current in opposite directions relative to one another. The measured short circuit current values for the first layer iron oxide and the first layer iron chromium aluminum alloy plates were 24.2 microamps and 24.7 microamps respectively. The short circuit current is a current through a solar cell when the voltage across the cell is 0. This result is significant to this study because the short circuit current is the largest current which may be drawn from the solar cell. Observation of non-zero short circuit current values between dark and illuminated conditions confirms that the plates made during this study were p-n-type semiconductors. The differential short circuit current as a function of time found using chronoamperometry using the same plates provided further support for the observation of photocurrent. This data is represented in figure 3. The plates were in dark conditions from 10 to 20 seconds, in illuminated conditions from 21 to 40 seconds, and in dark conditions again from 41 to 50 seconds. When illuminated, the plates consistently yielded lower short circuit current values than when in dark conditions. The data represented by figure 3A agrees with figure 2. However, the data present in figure 3B does not agree with its counterpart in figure 2, and this was an unexpected result. The yellow data set measured using the plate with the iron oxide layer deposited first was expected to yield current in the positive direction. We are conducting further studies to elucidate the cause of this unexpected result. In conclusion, the short circuit current values measured in solution provide strong support for the successful fabrication of a photovoltaic semiconductor p-n-type homojunction using all metal oxides as p and n-type materials. Future directions of this study should entail applying thinner metal layers to the plates so that a functioning, fully solid-state circuit can be made. This project would not have been possible without the help of Dr. Rowley, Dr. Farr, the E.L. Weingen Foundation, the Mary Alice Foundation Incorporated. Additionally, this project was made possible by the Integrated Lab program offered here at Carroll College. Integrated Lab is a class that allows undergraduate students to apply theories from physical chemistry, instrumental methods, advanced organic chemistry, and advanced inorganic chemistry courses during research in a multidisciplinary fashion. Thank you for your time and for listening to my presentation.